Alright, welcome. So this is going to be a video on ratios in similar solids. We have looked at similar figures before when we were looking at similar triangles, so we're going to be working off some of those ideas. These notes are actually going to be in 3 separate videos, so make sure you watch all 3 to get all of these notes in. Alright, so looking at this first part, it's just going to be some essential knowledge, so just some review that we've looked at when we did similar triangles. So the first part is going to be just determining to see if these solids are similar. And in order to do that, we are going to look to see if they have the same scale factor. We have worked with scale factor before, all right, and it's essentially the same idea. We're just going to compare the corresponding parts of each figure and see if they reduce down to the same fraction. So looking at this one, we want to compare the width to the width, and the length to the length, and last but not least, the height to the height. All right. So looking at the first part, we have our width to our width. So we have 18/6. And then we're going to look at our length to our length, which is 60/20. And then the last one is our height to our height, which is 36/12. Remember, just like in similar triangles, you have to stay consistent with which figure you put first. So I did the bigger figure on the top and the smaller figure on the bottom. So just make sure to stay consistent with which one you put first. All right. So once we have all of those corresponding parts together, we are then going to see if they all reduce down to the same fraction. And in fact, they do. They are all 3/1 or 3:1. So they have the same scale factor. And so yes, since they have the same scale factor, that means that these pyramids are similar. Alright? So I want you to go ahead and pause this video. Try the second one on your own. And when you feel comfortable, you can come back and see if your answer is correct. Alright, so I hope you were able to check to see if these prisms were similar on your own. So again, we're going to compare the length to the length and the height to the height. Now, it's only 2 in this case. Okay, so I'm going to stay consistent with putting the smaller one on top this time. So we have 10/30 in this case. And then for our heights, we have 8/32. All right. 10/30 is going to reduce down to 1/3. And 8/32 is going to reduce down to 1/4. So they do not have the same scale factor. I'm going to just put SF for short, which means that no, these prisms are not similar. All right, the last thing we're going to cover in this particular video is just the baseline. We're going to use this idea the whole time that we are doing ratios in similar solids. All right, so this is finding the ratios for either the scale factor, the area, or volume given one of those ratios. So how this is going to look, we're going to set up a chart. So we're going to have linear, then we're going to have area, then we're going to have volume. All right, and under each one of these, we're going to put their corresponding ratios. So if you're looking at linear, you're looking at something like the height of something, or the length of something, or the width of something, or the radii, or something just linear, all right? So that is going to be our A to B ratio. All right, we only have one thing. But when we're looking at area, we start comparing two different things, all right? So maybe like the base and the height. So we're multiplying two things together. And whenever we do area, on our units, we always have a squared with it. So our area is always going to be the a squared to b squared. All right? And then we have volume. So volume is multiplying three things together now to get our volume. And whenever we look at our units for volume, it's always your units cubed. So this one is going to be a cubed to b cubed. All right? And we're going to be jumping in between all of these ratios, okay? So how we're going to jump in between those is just like we would whenever we were doing special right triangles. So we had this same sort of chart set up whenever we were doing special right triangles, and we would move forward or we would move backwards. When we move forward in the special right triangles, we will multiply. Now, when we move forward, we're going to raise it to the power. All right. So we're going to raise it to the power of whatever we're ending with. Okay? And then, if we moved backwards when we were doing special right triangle, we would divide. But now, if we move backwards, we're going to take the root of whatever we started with. All right, let's try an example. So the first thing we need to do is set up our chart. So I like to abbreviate, so I'm going to have linear there. Then I'm going to have area, and I'm going to put a little squared with it just to remember that that is our squared units. And then I'm going to put volume and put a little cubed with it to remember that that one's our cubed units. So looking at the question, it says the ratio of the volumes of two spheres is 8 to 125. All right, so in the volume column, I'm going to put my 8 to 125. Okay. What are the ratios for the scale factors and the surface area? I read that the wrong way. What are the ratios for the surface area and the scale factor? So just like before, when we were doing this whole setup, when we did special right triangles, we always wanted to go back to square one. That has not changed. You always want to go back to square one. So we always want to go to the linear first. Whenever we are going backwards, that means that we are going to root whatever we started with. So we're actually going to cube root our 8 and our 125. So our cube root of 8 is going to get us 2. And the cube root of 125 is going to be 5. That actually gives us the ratio of the scale factor. So we know that the scale factor ratio is going to be 2 to 5. All right, we still need the ratio for the surface area. So now we're going to start from square one, and now we are going forward. But whenever we go forward, we raise it to that power of whatever we end with. So now we're going to square both 2 and 5. So our surface area ratio is going to be 2 squared, which is 4, to 5 squared, which is 25. So this one is going to be 4 to 25. All right, go ahead and pause that video for a second. Try the next one on your own, and then come back to see if you got it. All right, so now let's go over this one. So we have our chart. So we have L, A squared, B cubed. I made that one over a little bit too much. We are given the ratio of the surface areas, and we are trying to find the ratio of the scale factors and the volume. So here we're given that it's 36 to 4. So I'm going to put that 36 to 4 in there. Notice that we can simplify 36 and 4. So 36 and 4 share a common factor. So we're going to take out that common factor. Their greatest common factor that they share is 4. So I'm going to divide 4 from 36 and from 4. So this is actually going to be 9 to 1. I just simplified that ratio. Okay. And then just like we did before, we always want to go back to square one. Whenever you go backwards, you're going to root whatever you started with. So we started with squared. So I'm going to square root the 9 and the 1. So the square root of 9 is 3, and the square root of 1 is 1. So my ratio for my scale factor is 3 to 1. All right, so now let's find that ratio for the volume. So now we're going to go forward. Whenever we go forward, we're going to raise it to the power. So that means that we want to cube 3 and 1. So the ratio for our volume is going to be 3 cubed, which is actually 27, and 1 cubed, which is 1 times 1 times 1, which is still just 1. So this one is going to be 27 to 1. All right, go ahead and jump to the second video to finish these notes.